that you can only increase the distance, but you can also in fact contract, right? So I prefer dynamic scaling. And this has a -2 scaling factor. Yeah, number -2. Right, if you plug this back here, if you come back to the finite version and do a finite scaling, you see that it has the scaling factor for scaling transformations is the constant to the power of -2. Right? And just be careful when you're reading any conformal fluid theory text. Be careful. Just check at the beginning, because there are some people that define this with a square here. Right? It's just convention, right? I'm defining without the square. Okay. And now we have the term. I already told you what this is. This can only be the special conformal transformations. Alright? And to determine it will be that we have a 3 tensor here. So it will be that we have lots of special conformal transformations that we can do. But from this equation, we see that this C tensor has to be symmetric in its last 2 indices, right? Because it's contracted with the x squared here, basically, right? So we know that C has this property here, right? It's symmetric in the last 2 indices. And to determine the formula of this guy, we plug back into this equation here. Why? Because this is the quadratic part of the solution, right? And this equation 2 is has only 2 derivatives, so this is the only contribution that survives this equation. Alright, so that's how we determine it. So when we plug only this piece back into equation 2, we find this. So you see that this pretense is actually determined entirely by this combination here, by its trace in the first 2 indices. So we don't have naively you would think that you have in the dimensions d to the cube transformations here, but then we reduce some more because you know that they must be symmetric in the last 2 indices. And when you finally plug back into this equation, you realize that you actually have only the special conformal transformations here. Alright? So we usually define a vector B, and we incorporate this 1 over D factor, just for convenience, as the trace in the first 2 indices of this C part. So we find that these special conformal transformations are characterized by a vector, just like a translation, but of course they're not translations.
Where do you see that it must have D component? D?
Because when you have
You have to plug it in.
Yeah. In principle, you think, okay, I have D possibilities here, D here, D here. So you have D to the cube. Say we have 4 dimensions. Working 4 dimensions. So we have for the cube, like 64 special conformal transformations. But then you reduce this a little bit because you know that this guy must be symmetric. But then when you take this into account and also plug this here into equation 2, you see that you can solve for the tensor, and this is what you find. can check that this is symmetrical. The exchange of menu. Here the metric is obviously symmetric. And this guy goes into this and vice versa. Alright? And you see that the only combination that appears here is the trace in the first two indices. And the last index is free. So if I'm living in d dimensions, this is characterized by this vector. This vector definition. Right, so you only have d special conformal transformations. Okay? Any more questions? And the infinitesimal form of this transformation, that if you plug this definition here and substitute and bring this back here, you can find the infinitesimal form of the conformal transformation, the special conformal transformation, and it turns out to be I'm going to erase this one because I referred to this one a lot. When you plug back this, again, we take this, plug this definition here, just to make it simple, and we learned that the infinitesimal special conformal transformation actually looks like this. Right. This infinitesimal special conformal transformation. Right, so you see that's rather complicated. That's why you cannot visualize this with ease just as we do for the scale transformation. The finite version of this you can find by integrating the equation, the infinitesimal form. And this is a pain, but you don't actually learn much by doing this explicitly, so I'm just going to state the result. Right? And the finite version of this transformation is this one. If you want, you can check that if you do a infinitesimal version of this, you fall back to this. It's an easier route to check, rather than integrating the equation.
Those are special cases, because what are the other terms, like the translation and the limitation? Those are special transformation, like what are the other terms of the
You're saying the
transformation?
this one?
Like the translation, the rotation.
Oh, okay. Well, for the rotations and the translation, I don't know, right? Because from theory. But an infinitesimal translation is just, it has the same form, right? Just keep specializing. Okay, pick a translation here, pick a scale, pick a rotation, pick a SCT, and throw them back there form and just see the infinitesimal form. And the finite form of this is just, it has the same form. I don't know, I guess you just sum over all your infinitesimal steps. For the rotations, you have a matrix, right? An SOD matrix, for example. For the scaling transformation, you have actually you got to ask this because the scaling transformation, the infinitesimal version is going to be this will be the infinitesimal version of a scaling transformation. Finite version will be just like, I don't know, big lambda here. keep scaling your system. And for the special conformal transformations, that's already written up there. Okay. Any other questions? No? Okay, just for anybody else. The scaling factor for a special conformal transformation is alright, just again take these transformations and look at them here. Or you could easier, it would be easy to just use this F. Remember that F is Q over D. This is divergence, right? That's what I found for F. And since F is related to the scaling factor by this equation, then you can just choose any of these infinitesimal conformal transformations, plug them in here, the divergence, and just solve this equation for the scaling factor, and you can find it. It's just boring. You don't learn anything. You won't be having any use for this, guys. It's just like sitting. So, or you will need to. It's alright. You believe me? The next step would be to find the infinitesimal general rates, but we don't have much time left. So instead, I'm just gonna, since you asked about the discrete transformations, I'm just going to tell you about the one discrete transformation, or at least the one discrete transformation that has any use in conformal transformations, which is resolve the continuous infinitesimal transformation that are connected to the identity. We have a discrete transformation. Which is the inversion. What it does, by definition, you just take a point x mu and you map it. This is the denoting, it's not denoting it, it's just denoting inversion, the inversion map. And this is by definition, it's this thing here. Just divide by its modulus squared. Alright? You can, from this functional form, you can already see why this did not arise here. Right? It doesn't have any Taylor expansion. Okay? So, but it does have a scaling factor. No, you cannot compute them. You cannot compute it by plugging it back here.
Why is that inversion?
What?
Why is this inversion? You don't.
Well, what do you expect for an inversion?
To revert, to have a minus sign, to revert one of the components.
A minus sign would be parity.
Huh?
A minus sign would be parity.
Okay.
That's included in the.
Okay.
You still have P and T here. It's included the just as you have for the points in the QFT in the Poincaré group. Of course, you also have. P and T, of course.
Okay.
They're here. But inversion, you can clearly see it does not reserve lengths. Okay.
Yeah.
So that's why they do not show up in the standard quantum field theory.
So yeah, it's like a scaling, but it depends on the point. So it depends on x. So
it just sends if you're really say this is the origin. And you're sitting really close here, you apply an inversion, then let's say the origin. One thing that people say about this, it's like the origin gets mapped to infinity. For example, and vice versa. That's why to study conformal field theory, you usually do it in the Riemann sphere. We add the point infinity to make all these transformations well defined globally. And in fact, If you look carefully into this special conformal transformation, the final version of it, you can have this thing can actually sense. There could be some sense.
In this inversion, if you have x squared greater than 1, then you're going to bring the point in this inversion. If x squared is greater than 1,
X squared will always be greater than Oh no, greater. Okay, no, yeah.
if it's greater than x squared, then you map the point. As you bring the point close to the origin.
Yeah.
And if it's less than 1, like it's space-like, and then you map it. So in that sense, inversion.
Yeah, that's it. It's like a multiplicative inversion, not like an additive
It's like an
inversion.
inversion with respect to x squared equals 1. The sphere, not exactly.
Yeah, you take the sphere, then the inversion like maps you from inside to outside the sphere, and so on. Okay. So that's you also read this a lot in conformal theories. You work in the Riemann sphere. Just mean we define as the remember we're studying conformally flat space, so you have a flat space and you have the point infinity to your manifold, and that's where conformal theory takes place. Just to make all transformation well-defined globally. And you could actually see that this, for some special values of B and X here, you could blow up the special conformal transformations too. So you need this point infinity to actually have a globally well-defined finite SCT. And yeah, the next step would be to find the conformal algebra, but we don't have
Special conformal transformation is like inversion plus
Oh yeah, that's this remark too.
translation.
Another way to understand the special conformal transformations is an SCT is it's inversion. This means composing, right? Inversion translation. Inversion. So we say that a special conformal transformation is a translation conjugated with it. It's on both sides, it's multiplying both sides. It's a inversion conjugated translation. Infinitesimally, it would be something like this. You could have x nu prime would be you first invert this guy. Okay. First you derive from first invert, then you do a translation, and then you just invert this guy again. If you do this, you end up with this. Alright? So special conformal transformation is like translation of the inverses, if you want. Okay, so that's kind of the reason why it's hard to picture what they do, like actual picture. But this makes it more intuitive. In fact, if you start only with the Poincaré group plus inversions, you take the Poincaré group and add only inversions, then you can construct the whole conformal group. Right? Because you first you construct the special conformal transformation, as we will see in the next lecture, from the commutation relations, then the scaling will just be produced. Okay? So Poincaré plus inversion generates on the conformal group.
This inversion, since it depends on the denominator on x squared, is not defined for like points. No, since the inversion you are divided by x squared.
The thing
so
is that this guy is positive, right?
Okay.
This guy is positive, but this guy is a scalar product. This guy can be negative.
No, but that discrete transformation, that inversion.
This here?
No. Yeah, that one is not defined for x squared equals 0.
No.
So you can. There's no sense on inversion.
Yeah. For x, if s okay, no. Yeah. Well, if you think microscopics, you have to take this into account. If you think Euclidean, this x squared equals 0 is just the origin,
Okay.
right? And x squared equals 0 in a Minkowski space is a light cone,
It's the light one, yeah.
right? And we'll see that we'll also come to this, I don't know if the next lecture of the other one, that the light cone is preserved by at least the conformal.
What's
The light cone gets back to the light cone by the continuous transformations.
But what's the interpretation that this inversion is like infinite for the light cone? There is some interpretation to that? Because if you apply it to a point in the light cone, it gets infinite. Maps to infinity. No, just pass
Yeah, I don't know if
pass it
that's
from my
any.
my mind. No, just curiosity.
Well, maybe what's confusing here is that I'm doing these two points, right? X squared being well, if we have to. Well, forget about this. Not worry. I don't know if there is any cute physical interpretation.
Yeah, I just thought it was weird because this transformation that you get from preserving the cone structure gives it's not defined. This is not defined for points in the.
It is defined because we add the point infinity.
Okay.
I mean that's the only thing. I don't know if there is some other picture that is more cute. It is well defined in the sense. If you work in the Riemann sphere, then this will be well defined. Okay. So like we would be contracting the light cone into a point. Infinity. But then we're gonna. That's it. It's real, but yeah, it's real, but that's what it's.
Okay.
Okay. There is I just mentioned, but there is a relation between inversion and parity in conformal field theories. And just to remind you that, just as it's under quantum field theory, you have to have invariance under the continuous transformation, right? These will have to be unbroken symmetry. And you can have quantum field theories that violate parity or time reversal or both. Like just take electric theory. It is not invariant under parity transformations. Alright? So there are no problems with parity in MT are violated in standard quantum field theory. So by the same token, not all CFTs will be invariant under inversions. Okay? But there is a result that if you have invariance under parity, then this implies invariance under inversion and vice versa. That's a relation between them, in the invariance and CFTs. But in general, they do not need to be actually realized in a generic conformal field theory. If you know they are, then you can actually call inversions and get some transformations. Make some computations easier because you could use this. So you have a general CFT that you know that's invariant under inversions, and you want to do a special conformal transformation. Then rather than doing this, you can just do this like step by step, which is a bit easier. If you know inversions are symmetry of that specific conformal field theory. If it is not, then okay, you have to do that. Okay. Any more questions? I'll just end here. In next lecture, we will find the generators, find the algebra, make some. When we get the algebra, we start to understanding a few things I said in the motivation about the representation, about the nature of the eigenstates in conformal field theory, and we'll maybe have time to see some of its consequences for field theory. Alright? Any questions?